Okay, so in this one we're looking at Newton's 3 laws of motion. You should be pretty familiar with them by now, so we're just going to have a brief run through them. Okay, so Newton's first law is called the law of inertia, and basically what it states is that an object will stay still or keep moving at the same speed or the same velocity or with the same velocity until an unbalanced force acts upon it. So the key word here is unbalanced. It needs to be an unbalanced force in order to cause some sort of change in motion or in order to cause an object to begin to move. So in this example that we've got here, so we've got a truck, and in the top example, we've got forces of 100 newtons acting on it from either side. So a forward motion, 100 newtons, and a backward motion, 100 newtons. We also know that there's the upwards push from the road and the downward push of gravity. So this truck here, staying still, and we've got balanced forces. In the second picture, this is obviously where an unbalanced force has acted on the truck. So you can see here at the front, 60 newtons, a much smaller force. So this could be, for example, air resistance. And then at the back, you've got 100 newton force, and that could be, say, thrust, for example. This causes the truck to have a net force of 40 newtons, and it causes the truck to move forwards. These are unbalanced forces. There is a difference between this force, between the value of this force, or the numerical value placed on this force, and the one that is pushing against the truck or against the motion of the truck. Okay, so basically what inertia is the tendency that objects have to resist changes in their motion. And an example of inertia when we're talking about cars, for example, is when you turn the corner. So if you're traveling along in the car, but you actually have your own forward inertia. So when the car turns right, for example, your body wants to keep going left, which is why we sort of feel this jerkiness whenever the car turns. And then as the car turns, your body slowly adjusts and comes back in line with the car, but you have your own inertia. That's why when cars brake suddenly, people who are not wearing seatbelts will go through the windscreen because they have their own inertia. Your body is resisting changes in its motion. It has its own velocity as it travels along with the car, but because when the car brakes, your body has a tendency to resist that braking, so that's what causes you to go through the windshield. Another thing that you need to remember is the greater the mass an object has, not the weight, but the mass, the amount of stuff in it, the more mass an object has, the more inertia it will have. So a truck, for example, has more inertia than a small car, for example. Okay, so Newton's second law is force equals mass times acceleration. So force, big F, just change this pen colour. So force measured in newtons. Okay, and when we talk about force in this example, we're talking about net force, okay? We're not talking about picking a force, because as you know, on an object, for example, there could be several different types of forces. When you're driving along in the car, there's friction, there's thrust, there's air resistance, there's gravity, there's the upward push of the road. So you have multiple sources of force acting on that car, but we're talking about the overall net force. So in the previous example, we had 100 newtons and 60 newtons, so the net force was 40 newtons. Now, A is acceleration. We're obviously measuring that in meters per second squared. And mass, we're talking about kilograms. Okay, so because this is a formula, there are relationships between the different variables. So for example, if I have a ball with a mass of 1 kilo and I exert a force of 2 newtons on it, my acceleration will be 2 meters per second squared. However, if I have the same ball and I exert a greater force, so I exert twice the amount of force on that ball, then my new acceleration is 4 meters per second squared. So, if I double the force, I double the acceleration. The way that we express this relationship is force is directly proportional to acceleration. So if I quadruple the force, so if I have 2 and then I have 8, and then I have 8 here, so then I have 4 times the force equals 4 times the acceleration. And obviously this only holds true if I'm keeping the mass constant. So I'm keeping the mass constant at 1 kilo. If I change the mass, then this rule does not necessarily apply, because we'd be talking about different objects. On the other hand, when I'm looking at mass, for example, if I keep the force at 1 Newton, and I keep that constant, and I have 1 kilo mass, and I want to work out what the acceleration will be, my acceleration will be 1 meter per second squared. If I halve this mass, so if I have 1 Newton equals 0.5 times A, 0.5 kilograms times A, my A actually doubles, because 1 divided by 0.5 is 2, so my A actually doubles. So the relationship, or the mathematical expression that we use to talk about this relationship, is that A is inversely proportional to mass. So if I have half the mass, then my A will actually double, as shown by this example. Okay, so the types of forces that we're looking at in this unit includes air resistance, which we're going to have a look at a bit later, friction, big one, weight or gravity. You have the forward driving force. In a car, you have a thrust from a really large engine, from a combustion engine, for example, in a rocket. There we're talking about thrust. Generally moving in a forward manner. Okay, so friction. If we're talking about being in a car, and this is my car, excuse my bad drawing. Okay, so friction, 2 windows in a car. So friction is, we find it here as the wheels move over the road. So friction is defined as a force that is exerted by a surface as an object slides across it. So the force is actually exerted by the road as the wheels move along it. The amount of friction depends on the surface. So if the surface is rough, there's more friction. If you slide a book across a table, for example, and compare it to a car moving along the road, there's less friction between the table and the book than there is between the wheels and the road. Often, if there is a lack of friction, that's when we can see car accidents. So, for example, if the road is slippery or wet or there's snow, you can see a loss of friction, and that causes the car to career off and causes the driver to lose control. More often than not, friction opposes the motion of the object. So the car is moving this way, and friction is opposing it, going in the opposite way. So it's kind of like a conveyor belt where the things are going forward but everything else is going back, but the conveyor belt underneath is moving backwards. Okay, so air resistance. It acts as an object as it moves through the air. So if this is my rocket, Okay, air resistance going this way. Pushes down against it. So air resistance opposes the rocket's motion. So upwards we have thrust, downwards we have air resistance. So it's most noticeable for objects that travel at high speeds, like rockets or planes, for example. We don't normally consider it when we're talking about cars, but air resistance is the force that sort of goes over the front of the car. So if this is like my windshield, air resistance is the thing that's going, opposing the driving force, which is going this way. Now, obviously, these aren't the only types of forces. These are talking about land-based forces. You can also have something called drag, which is very similar to friction. Normally, we talk about drag, we talk about air drag, or even in water, we talk about drag. And it's still the same thing, still opposing the motion, going backwards when we want to go forwards. Okay, so see this person, he is obviously sitting on a chair. He's telling you that he's sitting on a chair. So basically what Newton's third law says is for every action, there's an equal and opposite reaction. Okay, so if this person is sitting on a chair, it goes, therefore follows, that the person is exerting a downwards force on the chair. From our knowledge of, say when a car is driving along, we know that the road pushes up against the tyres. That's what allows the car to move. So following that same logic, it follows that there is an upwards force. The chair is applying an upwards force to that person's butt. These two forces are equal. So the upwards force of the chair on the person and the downwards force, or the weight that the person is putting on the chair, is an equal force. Okay, so what does this example tell us of the chair? So every interaction there's a pair of forces. Acting on two interacting objects, so always two objects. Now, the size of the force on object 1 is the same as the size of the force. Okay, maybe that's F's a little bit too big, but let's try again. On object 2, they're always equal. So the F's are always the same, but the direction is opposite. So in the chair example, the person is exerting a downwards force and the chair is exerting an upwards force, equal to each other but in opposite directions. So basically this tells us that forces come in pairs. We call them equal and opposite, reaction, action pairs. So I want to give you one last example. So say I have a fish. So this is my fish. It's a really ugly fish. Okay? So I have a fish. And this is the water. Okay? So my fish is in the water. The fish's fins push back against the water to propel the fish forward. But the actual thing that helps propel the fish forward is the reaction of the water pushing forward against the motion of the fins. So fins push backwards, water pushes forwards in an equal magnitude. So that's another example of Newton's third law.